lectures of offshore positioning in Geodesy and Geomatics Engineering of Institut Teknologi Bandung, or ITB. We're going to talk in this module about the inertial applications in module 11. So we're going to delve about the types of inertial navigation sensor and how we use the inertial navigation system in our real-world application, for example, like how we mount it, how we install it, how we do the calibration, and how the applications really looks like. So yeah, welcome again to the lectures, and I'm Fikri Muhammad. I'm happy to share the lectures with you guys all. All right. First, we're going to talk about the types of the inertial navigations. We previously talked about the IMU sensors, and basically in the inertial navigation system, we're going to have to discuss about two types of the inertial navigation system that commonly used by the real-world applications. But yeah, for a reminder, we have to note that the inertial navigation system, or INS, provide the positions, velocity, orientations of the vehicle, or like AUV, relative to the global reference frame, or for example, the ECF or the inertial frame, or any frame that you refer to. It can also be a navigation frame, or it can also be the body frame. Yeah, depends on what you need. So the INS, the inertial navigation system, it's a system, right? In the system, we will have the sensor. The sensor consists of gyroscope and accelerometers. And if you choose, both of the sensor will be having a sensor, basically the combination of the sensor, which is the inertial measurement unit will be having the unit, the inertial measurement unit, or the IMU. IMU consists of the gyroscope and the accelerometers. Can be also using magnetometer as an additional sensor to compute the heading. As we know, the gyroscope and accelerometers both compute the motions, basically at the end, or the orientations, that later on it can be integrated to derive the positions. All right. First, we're going to talk about the gimbal-based INS, or stable platform INS. This is stable platform because it plays inside the gimbal. As we can see from the picture here, we have the accelerometer sensor and the gyroscope sensor. Yeah. We have the accelerometers and the gyroscope that mounted or installed into this stable platform, or the motherboard, for example. The motherboard, which is placed in the stable platform. It's stable platform because it's placed inside the gimbal, as we know from the spinning mass gyroscope, which is also has the gimbal to stabilize or measure the rotations based on the spinning mass. This one is somehow the same but slightly different because all the sensors are mounted inside the gimbal so that it always aligns into the global reference frame, or the ECF, for example, because the gimbal try to always align it with the global reference frame. Like, for example, depends on the gravity effect, like pointing downwards, so that it will try to always referencing to our reference frame. Yeah, by placing that inside the gimbal, it will always reference to the global reference frame, and when we try to move our sensor that place inside that place to our body, for example, to our AUV, the AUV will directly measure the linear accelerations or the orientations, all the global orientations based to the global reference frame because it's directly measured the changing that refer to the global reference frame, right? So it doesn't try to detect the movement of the body itself, because the movement of the body is already compensated by the gimbal, so that we don't have to compute again the uh, other angles based on the body or the motions of the body, which reduce the computation time later on, right? So if we don't have to compute all the other angles or the motions estimations based on other angles, then we will having reduced computation time. Yeah, because all that have been compensated by the gimbal. But of course, it has limitations because it's a mechanical part. Yeah, it might have limitations later on if the parts wears out, or if all the gimbal align to one axis, it might uh, presenting the gimbal loss problem. All right. The second one is the strap down INS, which is most covered and most common, and also uh, globally found in our system. Like for example, in our handheld system, in our mobile phone, it's strapped out because it's mounted inside the motherboard. For example, all the gyro and the accelerometers see here. Accelerometers and the gyro are mounted into the motherboard, and the motherboard are placed or mounted rigidly into our mobile phone. So as long as the mobile phone moves, the gyro will be also moved, and means that it doesn't have the compensations like in the gimbal-based system, meaning that the uh, axis or the frame of the IMU will always align with the body frame. So it doesn't align to the global reference frame, for example, here as long. And yeah, as long as it doesn't align to the body frame, when the mobile phone moves, which has the IMU, when the IMU moves, the IMU will follow the body frames, doesn't follow the global reference frame. So that we have to, yeah, later on define the relationship between those two frames first, and then we also have to define the motions first, because later on we want to align that, we want to transform the motions of our body to the reference frame, right? So as we discussed in the previous module, we have first to define the other angles so that we can define the motions of our body, of our mobile phone, or our UAV or AUV for working on the water, right? So yeah, well, in summary, in the gimbal INET, we have uh, lots of large, expensive precision mechanical parts. It's basically mechanical parts because it relies on the gimbal movement to stabilize the movement of the vehicle, of the AUV. But yeah, of course, it can wear us out, or the mechanical part can wear us out over time, or jam, and vulnerable to gimbal lock. So what is gimbal lock actually? We'll talk about that later on. Yeah, and simple like all navigation algorithm, because the movement of the body is already compensated by the gimbal system, so it doesn't require much computation resource to calculate again the relationship between the body to reference frame. And yeah, commonly used in expensive system like spaceship, aircraft, submarine, and the other things you have to figure out. Okay, then you can also finding out. But yeah, basically it's very expensive. We could also mount it into our AUV to have the precise motions or precise positioning estimations at the end, but still it's very expensive. Yeah, commonly we are using stripped out INS to the autonomous robots like AUV, drones, mobile phone, USV, and yeah, because it's small, cheap. Can you imagine if we have like $50,000 price for only for the a stable platform INS for our mobile phone. And yeah, uh, and our phone is only having price about 1% of it, maybe even less. So doesn't make really any sense to put the uh, expensive stable INS platform. Yeah, but again, it will require more complex navigation algorithm because we have to correlate between the movement of our body, of our platform, AUV, for example, because it's basically measure the motions of our body and determining the Euler angles, and then correlates the motions based on the Euler angles to our Earth uh, frame. And of course, it requires more computational resources. So what is gimbal lock? We're going to talk again. If we're going to go back again to the gimbal lock, so the gimbal lock is basically the gimbal using three three rotational rings, for example, or three nested rings, and each of them capable of rotating around one axis. Yaw, pitch, yaw, pitch, and roll, as you know. And when to access a line, like here, uh, the system can no longer distinguish certain rotations because, yeah, it's losing the ability to track or control the motion in one direction. So basically, for example, when you uh, considering the spacecraft, for example, with three gimbals representing pitch, roll, and yaw, if the pitch gimbal rotates by 60 or 90 degrees, the yaw and roll axis become aligned. So the yaw and roll axis become aligned like this. And any further rotation around one of, so if the spacecraft rotating only one, for example, only in roll, it might be able, uh, it might not be able to distinguish which rotations currently the spacecraft is experiencing. For example, if the spacecraft is only having the rotation within the roll axis, it might also detecting the rotation within the pitch axis because it's somehow aligned. All the rings are somehow aligned. So the impacts, of course, the consequences of this gimbal lock, the loss of control, and yeah, it might have difficulty in determining the orientations, might misinterpret the orientations of the system, right? And of course, the system failure. And to avoid um, adopt strap-down systems, or also using uh, we've discussed earlier, if we are using the quaternions, we can mathematically avoid the gimbal lock, unlike the Euler angle, because the quaternion doesn't really rely on a fixed sets of axes and can smoothly interpolate between the orientation, but we're not going to talk about that here. And yeah, or maybe we can also add the fourth gimbal to prevent the axis from aligning. But of course, it increases the mechanical complexity. Or we have to combine it with other sensors as well. We're not going to change it to strap down because it's cheaper and complex to derive the equations, which is also basically it's not as stable as the one that we have here in the gimbal. But yeah, we can integrate it with other sensors like for spacecraft, of course, we can integrate it with a GPS or underwater or AUV, we can integrate it with the pressures or camera or optical or lasers or also acoustics like Doppler velocity lock, EPL or USPL or etc. Yeah, as I said, the sensor are placed. So the IMU, basically the gyrometers are placed inside the platform, and the platform are placed inside the inner gimbal, and then the outer gimbal are attached. The outer gimbal is attached to the vehicle body, so the vehicle body, and the gimbal will always try to stabilize the vehicle movement so that it can always be referenced to the global reference frame. So for example here, the gimbal versus strap-down INS. Yeah, in the gimbal setup, as the vehicle rotates, the gimbal adjusts the AUV orientation so that the gyroscope can measure the global angular velocity relative to the inertial space, as we know, right? And means that the vehicle is rotating the strap-down system here, the frames will always follow the vehicle movement or the vehicle rotations. So the frames will always be changed when it moves during the course of trajectory. But in the gimbal-based system, the frame will always try to align to the global reference frame here. See here, this is the global reference frame. This is our IMU frame. The IMU frame will always follow the global reference frame. As you can see here in the AUV with the gimbal-based INS, the frames will always try to follow the global reference frame here. The axis will try to stabilize along the course of the trajectory. As we compare it with the strap-down INS, so you can see here the course of trajectory of the frame or the axis will always be following the AUV. See here, yeah, the axis, for example, the red axis, try to follow the heading of the AUV, right? In comparison with this one, the axis will always be pointing towards the same axis as the global reference frame. All right, so in summary, the gimbal versus strap-down INS, as you can see here, we have basically the comparison between them. Basically, in the stable platform INS uses, as we know, it uses the mechanically stabilized platform or the gimbals. So it's basically in the concept theory, it reads the accelerometer readout that measures the specific forces acting on the system. Like for example, when it accelerates, it basically reading this acceleration. And the gimbal angular readouts provide the orientation data, determine the directions of gravity relative to the platform. And yeah, and this gimbal angular readouts will directly showing the global orientations because it's basically compensates all the movement of the body or the attitude of the body basically be ignored because it's already been stabilized by the gimbal. But yeah, of course, from the accelerometer's readout, we'll subtract the gravity component. The acceleration due to the gravity is subtracted from the raw accelerator data, leaving only the net accelerations or the raw accelerations in the global frame. And then if we integrate 2 times, we'll be having the initial positions and then deriving the global positions. So we'll be having at the end the global orientations and the global positions using the stable platform. So we doesn't have to do the combinations between the gimbal, between the gyro, for example, and the accelerometers. We don't have to do these attributions to at the first to derive what we need, which is the global orientations and positions, right? Difference with the strap down, as we discussed earlier in the previous tutorial, that basically both of the sensors are reading the motions of the body of the vehicle. And we have to integrate them with the sensor fusions so that later on we'll be having the global orientations and also the global positions. yeah, basically we'll be having global motions, basically the motions of the body that refers to the global reference frame. All right. We we did talk a lot about the IMU, INS, and which is consisting of gyroscope and accelerometer to derive later on the motions of the vehicle, right? And one notable mention that we also have to know is the Institut Heading Reference System, or the HRS. So it's somehow similar with the IMU or the IMS, but in the Institut Heading Reference System, or the HRS, it's only aiming to determine the motions of the body of the vehicle. So basically the inertial measure unit, we know that already. It has two sensors like accelerometer and gyroscope, which is placed on the onboard processing units. So this is the IMU, and the AHRS is basically somehow the same. It includes the IMU and the processing systems, basically because the processing system is needed to compute or collect data that measured by the raw accelerometer and the gyroscope to provide the attitude of movement of the vehicle and also the heading. If we integrate also the magnetometer from the raw data. Yeah, and basically from these two, from the IMU and the HRS, we'll be having the inertial navigation system. In navigation means that we also derive the position by integrating the velocity accelerations and also integrating the orientation inside our accelerations. Yeah. So yes, basically it's AHRS, but also including the positions and velocity estimations. So brief overview about our system, HRS versus INS. For the IMU, it has the heading sensor like magnetometers, but the most common one are accelerometers and the gyroscope. In HRS, we have additional processing on board system. So it's basically measure the movement of or course of movement of the vehicle in the trajectory course. And in the INS, we apply, for example, the filtering method to compute the movement of the vehicle, and also like, for example, Kalman filter, complementary filter, Gaussian, or any other filtering basically to derive or to estimate the position later on, and also the motions of the vehicles. So here, for example, the NS trajectory is basically measuring the trajectory of the vehicle in one course, for example. And the HRS is basically only measuring the orientations, or it's able to measure the orientations. And if we're applying the HRS to our computations with our filters, then we'll be later on be able to estimate the positions, which is the INS. So it's basically INS is also the HRS. The HRS doesn't mean INS because HRS is basically measuring the rotation, only the motions of the vehicle. But the INS measure both, measure the motions and also the positions estimations. Right. If you're talking about the sensor that used into our INS system, of course we'll be having the sensor specification. For example, here is the most common sensor specification that we're going to talk is about the range and resolutions of the IMU, for example. So it's basically the capability of the sensor, like the range is the minimum and the maximum input values sensor can measure. So how is the maximum of the range that the accelerometers can measure, for example, plus minus 2G, where G is 9.8 meter per second quadrant, for example. So outer than that, the accelerometers may not be able to measure anymore. But it's rarely common in the real world application. But in the spacecraft, of course, it will be experiencing different G if it goes to another atmosphere differences, and also uh, going from where, for example, we have 1G and then the outer space will be having, for example, outer plus minus 2G, then the normal MU, like strap down one, will not be able to measure the accelerometer anymore, which is why the gimbal-based system or more expensive one, sometimes it has more ranges, and yeah, sometimes it's more expensive because of that. Yeah, and yeah, basically the sensor will not measure or anything outside the range, and the resolution is the smallest measurable change of the sensor can detect. For example, the range is about 250 degree per second. For example, here, as you can see, between the discrepancies between the true signal of the vehicle movement, for example, between the 2G and the range. So outside that range, the accelerometers or the IMU cannot measure anymore at the range. You can see here when it has larger range or greater resolutions, lower range and lower resolutions, it might affecting how our data can looks like. So our data will look more seamless if you're having larger resolution, of course, and also larger range. But yeah, uh, larger resolutions really matters. Data sheets before we use our sensor in the first place. So the first thing that we have to consider is, of course, the range and the resolutions. So if it's applicable to our system, for example, so if we are going to use the ROV that will be working in different uh, water property state, for example, between the different salinity, and which also applying to different density and pressure, which of course the G may be a little fluctuative in those kind of areas, and we have to pay attention to that. If we want to have continuous estimations and more precise estimations of our IMU, of course, will leads to have larger solutions and probably also uh, larger range. And the other things that we have to consider is the bandwidth and the stable rate. Basically, the bandwidth refers to range of the frequencies that the IMU can accurately measure and detect. And it essentially defines how fast the sensor can respond to changes in accelerations and rotation. So basically, the bandwidth is defining how fast the sensor can respond to changes, like how when it vibrates in really fast vibrations, like for example, earthquake or seismics or any industrial grade that requires really rapid vibrations to be detected, the higher bandwidth may be necessary, like 1000 hertz or higher than 1000. And the sample rates or sample frequencies is from this. So the bandwidth is basically for every 1000 hertz, it can be collect 1000 data per second, like in solar, right? And for example, and in sampling rates from this 1000 hertz, from this 1000 measurement per data per seconds, sampling rate is basically how it samples or sampling frequency, how it collects the measurement, how it samples the measurement of the gyro and accelerometers basically in hertz. And if you're having signal with bandwidth of 100 hertz, you will need higher sample rate than that, or at least minimum bandwidth. So, but it requires to have more sample rate on the bandwidth so that it will have more accurate uh, sample for the signal. As we can see here in the pictures, we can hear the signal sample. As we can see here in the pictures, for example, when the signal sample at 1000 hertz with bandwidth of 2000 hertz will be having not seamless sampling rates. Here. Yeah. And in comparison with the signal that sample at or vice versa. Like the signal sample at in 1000 hertz with the bandwidth of 200 hertz, we'll be having more continuous signal that sample continuously. In comparison, for example, if we have a bandwidth, a larger bandwidth than the sample rate. So the bandwidth of the 200 hertz, for example, and we only have sample rate at 100 hertz, meaning that we can only be able to sample every 1000 hertz of data, which is, of course, there is a loss of signals that does not be considered by the IMU, which is why it's important to have more sample rate uh, for our IMU rate, for our IMU system, when we have specific specifications. Right. Next, we're going to talk about the uncertainty. Of course, we know about the noise and the bias, right? The noise and bias are the most common uncertainty that found in the IMU or in the accelerometers and the gyroscope. For example, in the accelerometers, it may have the thermal noise, like the variations in sensor components due to the temperature change. So it has to be noted that the alterations of temperatures, for example, if you're using the sensor continuously, of course, the sensor will be getting hotter, right? That's why the cooling system of this sensor is important to maintain the temperature changes over time. And the vibrations, of course, the external vibrations, like very rapid vibrations, will be challenging. Like if we don't have also very high uh, bandwidth or frequency to cope on that vibration, right? And the electronical noise, it's also can be found in the accelerometers, like the fluctuations in the sensor internal electronics. And the white noise, so we have to note this one, the white noise, because we're going to talk about it later on, like the noise with the constant power spectral density across all frequencies, leading to errors in acceleration measure. So it's basically random noise, but it has constant power spectral density. So it's basically random, but it's constant. Random but it's constant. It sometimes appearing in one time frame, but it has the similar value of noise when it also appearing in the different time frames when we are using the AM for our missions. In the gyroscope, we're going to talk about the bias stability. or the constant drift of the gyroscope 0 point over time. So in the initial error of our gyro, so when we are just turning on our IMU, we'll be having the bias stability, and then we'll be having the random walk, like the random process while the noise accumulates over time. Like, for example, because of the mechanical vibrations, electronical noise, or temperature changes, make noise into our gyroscope measurements, and this noise calculates over time and accumulates over time. We might call it as causing gradual drift, as we can from application module. If you have true values of measurement, of course, with the noise, we'll be having the gradual discrepancies between our true and our measurement, or the drift. And white noise, like in the accelerometer noise, the gyroscope can exhibit white noise, resulting in high frequency fluctuations in angular velocity measurement. Yes. So for example, this is different plots with different noises type. So for example, the red one is the white noise accelerations, and the green line is the random walk noise accelerations. And another noise, for example, Gaussian noise accelerations. So we have the acceleration plot, angular velocity, and position. For example, in position, we can see it clearly what the noise affecting to our measurement. As we see here over time, the noise make the discrepancy between each other, right? So because of the noises, we might be having difficulty in determining positions because it always drifting over time. Because of the noise that accumulated over time. Yeah, as we can see here, the random walk increasing gradually over time, which is also causing the drift. And the white noise and the Gaussian noise might be constant. It's always appearing constant, but it might be appearing, for example, in one time that value and other time frame that value, but it stabilizes constant plus minus values. Yeah, because of the random walk, the velocity rate of the vehicle movement may be drifting over time, but yeah, the white noise and the Gaussian noise exhibit similar behavior, like it's always increasing. It's always a constant over time, over the trajectory course in comparison with the random walk. Like it's really random, but it's accumulates over time, causing the drift. Yeah, drift either for positions and for velocity rate. And then the bias, right? We discussed about the bias previously. For example, the gyroscope or the accelerometers, like the IMU, but it's stationary or that's still in the initial position and level, the vertical axis. AMUs typically should measure the effect of the gravitational accelerations, which is the G with the red line axis here. The nominal value for derivative, for example, is 9.81. But if there's bias, like shown here, the graph with the blue line pointing downwards, it could report, the IMU could report, for example, 9.75 meters per second quadrant, which is, of course, a problem when we are going to use this for our measurement, right? On different kind of bias that found into our in our IMU, normally this is the bias in initial point of view or repeatability. When the IMU is powered on, basically when we in the time 0, for example, the initial bias can vary due to the several factors like temperature changes, sensor type, or any like vibrations or any signal processing algorithm, for example, that's used by our IMU. And yeah, repeatable bias is the bias that consistent, like, and yeah, because it's consistent, it's allowing us for more accurate calculation. So we can like we can determine the consistent values of the bias and then directly put that consistent value to our measurement or directly removing that consistent values in our measurement and our calculations estimations. And the variable bias that fluctuates, making the calibration more difficult because we need more time, different time frames to see the behavior of this variable bias. Right? But of course, still have the bias. For example, here we have the IMU measurements, and if because it's repeatable, the bias is always constant. We can directly measure the constant value and estimate the seamless movement or seamless measurements of our IMU. But if it's more random or more variable, we'll be having more fluctuate measurement over times in our IMU. So yeah, not that seamless in comparison with this measurements. And then, of course, during the IMU measurement, of course, we will also have the bias, which is stability or in-run bias. This bias refers to the variations of bias over time when the IMU powered on. When the powered on, of course, the bias will always be accumulated over time. And in the case of light-based gyroscope, like fiber optic or ring laser, we change in the physical properties like the optical length, yeah, how the lights performs over time that contribute to this bias strip, for example, here. So of course, during the time, the stable IMU bias, for example, in the gyros, in the light-based gyroscope, for example, will have the bias. So for example, we're supposed to have this true gravity with the green dotted line here, but because of the bias, because of the stable estimated bias, we'll be having, for example, the gravity measured as 10 instead of 9.8, which is somehow easy because it's linear to understand, but unstable bias requires more times basically to see how the behavior of the bias acting towards time frame. The causes of this bias stability is because of the forces, the applied force like the vibrations that apply to our IMU, and our IMU couldn't keep up with these forces. And then the using time because the IMU has been used for longer time periods, and then the increasing of temperature because the IMU have been using for long period of time during one run, and increasing the temperature to be hotter than the initial temperature state, will of course increasing the bias stability. But if we know how the temperature reacts, for example, the temperature increasing linearly over time, we can estimate that to our bias. But if we having the random forces or random mechanical stress, external forces, we'll be having more unstable bias during our course. Like when we are having causally external forces over time, like using time, temperature, or any stable movement, then we'll be having more easier calculation to define how our bias behave over time. But if it's more random, like external forces, then we'll be having more difficulties. But we can estimate the bias by having more measurements, by having more longer time period of measurement. So we collect more data, then we'll be having uh, for computational values to be added to our equations and to our IMU basically, and then the bias can be. The scale factor is also important. Yeah, the scale factor error refers to the difference between the expected output and the actual output of the IM sensor. Sometimes the units is described as a parts per million or percent. So how much percentage of the scale factor is uh, differs to our actual true value, for example. And yeah, because of the scale factor error of the AView instead of 9.8 meter per second quadrat, we'll be having, for example, plus 2% scale factor error. Yeah, but yeah, we can directly do the proportional scaling where the output deviates from the expected values. And yeah, we can just do the percentage deviations from the true values, basically just align this scale factor to our true values, and we'll be having the correct measurements. If we're having how much the scale factor of our IMU measurement is. So it's basically also somehow written in the product descriptions of the IMU. So these things has to be noted when you are choosing your IMU. Beside the bandwidth, the frequency, and the pepper rate, and the range and resolution. So yeah, the remarks, the effect of the ANS, of course, the noise can cause random fluctuations and short-term errors in the measurement, leading to uncertainty. And the bias introduces the constant offsets, which is, if it's not corrected, can cause long-term drift in positions and orientation estimations. And basically the other one is scale factor error causes a proportional error because the scale factor is already been defined by the data sheets of the IMU. So we can basically just align the scale factor. So the measurement so based on the scale factors. So that's yeah, but it's for of course leading inaccurate measurement, but it's consistent because the scale factor is already been defined over time. So it's basically we have to compensate the scale factor error. All right. So as we can see here in the pictures, the noise and the bias started in the initial positions and the scale vector, which is so applied. It's constant. Next, we're going to talk about the operations for our initial applications. Okay, we were talking about the types of the IMU that's commonly used, which is the gimbal base and the strap down one. So it's basically also defining how we install our equipment, our IMU sensor to our, for example, platform, to our AUV. But normally we have to place it in the center of the reference point, like the CRP of the AUV. But if we're not putting it inside our on our CRP or our center of mass, we'll have to compensate it with the offset. But of course, this offset will be also to correlate the transformations between the center reference point, like the frames, the center reference, which also defining somehow the frames of our AUV, so that later on we have to compensate between the concentration between the body frames and the IUV frames. Yeah, basically we have to align with the coordinate frame so that we don't have to consider these transformations or relationships between the body frames and the IM frames later on, right? And we can also so it has to be placed in the center, our IMU. And we can also put another different kind of sensor to integrate to our IMU. So that we'll be having more precise measurement to increase the accuracies of our INS. Because even in the expensive one, like the gimbal-based system, it might also be experiencing a problem when the gimbal locks its rearing, right? So of course, it has to be integrated with other sensors like meters, pressure sensor to detect the depth of the AUV under the water, and DVL, the Doppler velocity log, or other acoustic positioning system to improve the accuracy of our system. Like for example, when we're having lost a position estimations of our INS, we'll have to correlate with the DVL so that the positions will always be estimated to our IUV. Like for example, we can also rely on other sensors like meter, pressures, or barometer, so that every time we got lost in our position based on our based on the sensor, like for example, based on the IMU, will directly line it to our other sensor, so that the positions can always be continuously estimated. Because if the position of the AUV basically got lost, there will be a problem because it doesn't connect it to our onboard vessel on water surface. And if is that the case, the AUV got lost, and then we'll be losing our systems and basically losing also our data. And worse, we'll be losing our system. And sometimes this system is very expensive because it's also equipped by not only the inertial navigation system, but also other mapping systems, like for example, acoustic multi-beam, or also side-scan sonar, or forward-looking sonar, or any sensor underwater lidar, camera, etc., which is very expensive. But to mitigate, one of the things that we have to consider during the installation is of course the sensor orthogonality. Like we have to place, we know that we have to mount our sensor in the center reference point to avoid any transformations between the body frames of the IUV, between the IMU frame, so that the IMU frame will be mountly rigid and will be aligned to the IUV frame. So it's basically we're moving, we're calculating the motions of the IUV by using the IMU, not calculating the IMU movements that reference to the body frames of the AUV, which is more complicated. We want to avoid that, of course. But if we have a misalignment to our AUV reference point, for example, and we'll be having difficulty to determine later on how the AUV behave underwater, because basically all the measurement that derived by the IMU or estimated by the AMU are wrong, because the IMU is not properly aligned. So the IMU frame here are not properly aligned to the center reference point or to the to the body frames. And we can do the sensor fusions with not only gyro and accelerometers, but also with other sensors that we mentioned earlier, magnetometer, barometer, pressures, and other things. DVL to correct the misalignments, but we can also do the foresight procedures like offset estimations of these two sensors. So basically we do the offset measurement, but not directly, because we install the equipment, we install the IMU, and then we assumes that it's already perfectly aligned. It might not be. We cannot directly measure the offsets between these two frames because it's not visible. It's like we're mounting the GNSS and the multi-beam on just on the ships. Well, it's visible. We can directly measure the distance between them. But here we cannot directly measure the distance between them because we basically doesn't know how or where the center reference point of the AUV really is. It might be differs in the real world scenario, and the frames of the center reference point of the IMU. This might also be different. So we're assuming that we already installed the IMU in the center reference point, but considering that there's still assumptions of misalignment or the sensor orthogonality due to the installations, we can do the bore sighting procedure. So like this one, so yeah, the misalignment can cause error, of course. What is the bore sighting procedure actually, or also the estimation? So yeah, so the platform, so how the process of the bore sighting, basically the platform is often moved or oriented in a controlled way. Basically, we're going to move the AUV that already have the IMU installed inside the AUV body inside it. We're going to move the AUV towards 3 axes to describe the motions of IMU in 3 different axes, X, Y, and Z. And the collected data is analyzed to estimate the angle of misalignment, basically. So yeah, we're moving the AUV towards 3 axes, and then the collected data from this movement then can be analyzed to estimate the angle of misalignment of its of the if the IMO really have correct installations reference to the body frame. Yeah, it's basically calculating the relationships between the body frame to the IMU frame. So body frame is defined as 000, and then the IMU frames can be measured if we are moving the vehicle towards 3 axes. So how is the movement? So basically we're moving towards that axis and toward that axis and toward that axis. By doing so, we'll be having the 3 measurement based on the 3 axes, and then we can align that measurement, basically the measurement of gyroscopic accelerators to the initial positions of the body frame, which is 000. And yeah, other things that has to be considered or normally considered in the calibrations or the installation procedures doing the calibrations. We can do the calibrations by using the bore sighting, and then from that measurements we can do the calculations of Allen variance or AFAR. It's basically the two sample variance, and it's basically measuring the stability of the IMU over different time frames that developed by the Allen. So it's called Allen variance. Different time scales. So as it's shown here, it has different time frames from 0 and then 1 second or initial positions, and 100 seconds and 1000 seconds and 10,000 seconds, and etc. etc. But it's showing gradually somehow in the same time scales, the same scale, right? Even though the time frames is largely difference between one values to another one. So it's basically detecting the bias between these time frames and collected all the bias between the time frames, and yeah, see how the bias reacting, and also the random walk, and also the noise and bias reacting within this large time frame. But we separate this time frame within different blocks of time frames so that we can see the bias and the in-run bias stability over time frame, because we're having basically large or, or long period of time of measurements. We can see how the bias stability works and how the bias stability behave between this long period of time, how the random walk we have in the initial position, for example. So it's basically this graph plot as a log graph, where the x-axis represents the everything time or tau, and the y-axis represents the ln deviation or sigma tau, or somehow it's also called sigma tau, or ln deviations. Yeah, the steps is basically we're collecting the data. Besides the bore sighting, we have to like mount the IMU rigidly inside our AUV, right? But to avoid any thermal disturbances or temperature changes over time, temperature have to set to constant. Like the IMU has to be placed inside the thermal chamber, and the data log at high rates for extended period of time. Like for example, several hours. You can see here it's almost 1,000 hours for 2,000 seconds, or 2 to 3 seconds, but sometimes it's also up to 24 hours to have more uh, longer period of time. And then with this longer period of time, because of the IMU, we can see, even though the IMU stands still, we can see then the initial bias. When the IMU powered on, we can see the initial bias behave. And then during the course of time, during the running time, for example, when it runs for about 5 hours, we can see how the in-run bias stability is. And then later on the white noise, if it runs in the longer period of time, and then you can see also the random walk. And then yeah, we basically plot the Allen variance. So we need to have basically longer period of time for Allen variance plot, so that we can see how the bias random walk, when the white noise, the noise and the bias really behave in our IMU. If we only having, for example, 1 second, or here 100 seconds or 1,000 seconds, about 20, 15 somehow minutes, then yeah, we'll be having difficulty in seeing the bias really behave in our IMU, because the time frame is so small comparison with 1,000, comparison with 10,000 or 100,000. Yeah, the common uh, behave of the IMU in our Allen variance plot is somehow this. First, we'll be having the random walk at minus half tau. Then we'll be having the bias instability during the course. And then we have the rate of random walk. This normally it behaves like this. It goes like a bowing shapes over tau axis. So for example, here the calibrated IMU for gyroscope and accelerometers. So it's basically we want to know how the noise and the bias values for our IMU, right? And then by by extracting those values to our IMU measurement data, will be then later on uh, considering these values based to our measurement data, so that later on we'll be having more accurate measurement to our IMU, right? Because we consider the noise and bias already. We know the noise and bias already. We put that values to our IMU, so that later on when we are measuring our IMU, for example, if you're having the 1,000 meter per second quadrats, we'll be having, for example, the bias of that, for example, 1 meter per second quadrat bias and noise, for example, then instead of 100, we'll be having 99 meter per second quadrat. But as we can see here, the period of time is only up to 1,000 seconds, which is not that long. Of course, we can see the how the noise and how the random rate, how the bias and noise really looks like in our eye view, but of course it's not that much accurate because the measurement that's collected into our eye view is not that long in considering in comparing with another longer different time frame. Well, yeah. At the end, for remarks, for example, will be this is the applications like when we are tasked with designing and analyzing the navigation system for INS of an IAV, for example. We know that the AUV IMU provides raw accelerometers and the gyroscope data at a sampling rate of 100 Hertz. So it's not that high, but of course, but okay, we consider that the sampling rate is 100 Hertz. However, the IMU of course exhibits noise and bias and misalignment errors like here, the center reference point of the IMU, the frame of the IMU is not directly aligned with the IMU frame. And yeah, what to do? How to first consider the noise and then the misalignment and all the errors so that later on when we deploy our IMU underwater, we are sure that our IMU is already accurate enough to perform the inertial application. First, if you are considering that as a stripped down INS, that estimated motion orientation in line with the frame, of course, we're going to talk about the distribution between the gyroscope and the accelerometers. Like, yeah, it's like in the previous video. So we're going to apply with the filtering techniques like complementary filter or Kalman filter or any other filter. And then we compare the estimated orientations to the triangle. And then from that, only from that we can then get the brief information of how our INS behave and yeah, what kind of noise and bias that we'll be having later on. And of course, we have to analyze the uncertainty, the noise, and the bias. And we have to quantify the drift in a position and orientation due to accelerometers and the gyroscope biases. Of course, it's always accumulated over time and analyze the effect of noise and misalignment in motions occurs over time. But yeah, to analyze this uncertainty, of course, we have to do the calibrations so that later on we are sure that we'll be free from this at least uncertainty. But of course, it will be if we still have the random walk, like because of the external forces, of course, the drift will be still appearing, but yeah, we can reduce that by doing calibrations. First is doing the bore sighting, like yeah, moving the AUV or the IMU basically into towards three axes. Yeah, to derive the rotation matrix between the misaligned IMU frame and the AMU frame. And we record the IMU when it stands still. We put the IMU, for example, on table, and then we record the data for long time period, for example, for 1 day, 24 hours, and then analyze and identify the white noise, bias, and stability, basically characterize the noise. And then we subtract the bias from the Allen variance and other deviations or how to put that to our IMU data so that our IMU data measurement or our IMU raw measurement data will be incorporated with the noise and the bias that extracted from the Allen variance. All right. Yeah, I hope I will give brief information about how, if you want to use our IMU to do the inertial navigation system for positioning estimation underwater to AUV, basically for offshore positionings, because it's so common that the underwater robotics are using this IMU sensor or the inertial sensor, but of course it's sometimes also integrated with other sensors. All right. Yeah, I hope you can get some insights and informations about the inertial navigations, what the types, about what to do if we are going to use the IMU, calibrations, and how we install, how we choose the system, what kind of parameters that have to be known before we are selecting the system, basically. Uh, because it's always be written in the datasheets of the IM. So what is important for us to know, and later on we can then estimate how accurate our system really is if we're going to use it in offshore position. Thank you. I hope you enjoyed the lecture, and until next time.